Here we have a graph, and the problem tells us to assume that it's the current and not the voltage as shown in the original graph, and that the peak value is 100 microamps. So that value is 100 microamps. And we have a 0.2 millifarad capacitor, and we were told the initial voltage on the capacitor is 0 at time t equals -4 seconds, and we're supposed to determine and plot V of t. So the first thing we can do is to remember how you get the voltage from a graph of the current across a capacitor, and the voltage is the voltage at time t0, or whatever time you're starting. So voltage at t0 plus 1 over the capacitance times the integral from t0, wherever you're starting, to t of I dt. And this gives us a function in terms of t, because this last part here, the integral, that integral is a function, so it'll give us the voltage at time t. If you just want to know what the actual number voltage is at a particular point, then you can calculate the integral as a definite integral. You can just come up with what the number is. And we're going to actually need the voltage at a few points later on, and so we'll do that right now and get them. We can find later that there's another way to do it, but we're going to get what the voltage is at -4, -2, 2, and 4 just by looking at the graph and considering the integral as the area under the curve. So we know that the voltage at t equals -4 seconds is 0 because that's given. So we can go ahead and say V of -4 equals 0. Well, now let's look at V of -2. So V at -2 equals, and we'll use this equation that we have up here, the one that we know, which is -4, V at -4, plus 1 over the capacitance times the integral from -4 to -2 of I dt. So the voltage at -4 is 0. The capacitance is 0.2 millifarads, and just make a note over here that 1 over 0.2 times 10 to the -3rd is 5,000. So we can use that every time we need 1 over c, we can just say 5,000. So plus 5,000 times the integral from -4 to -2 of I dt. Well, integral is just area under the curve. So that would be this area that I'm shading in right there. So that would be 5,000 times 1/2, and the base is 2 seconds, and the height is 100 microamps, so 100 times 10 to the -6. And I get that I have written down here that that is 0.5. Okay, now let's get V at 2. So I know what V at -2 is. So now to get V at 2, I can say that's the same as V at -2 plus the integral from -2 to 2, well, 1 over c, integral from -2 to 2 of I dt. Well, V at -2 we just found was 0.5. Plus 1 over c is 5,000. And now we need the area of this rectangle. So that will be, our base is 4 seconds, and our height is 100 microamps, so 100 times 10 to the -6. And I have that ends up being 2.5 volts. And now let's get V of 4. So V of 4 will be V at 2 plus 1 over c times the integral from 2 to 4 of I dt. Well, we know V of 2 is 2.5, we already had that, plus 5,000. And then this triangle has the same area as the triangle that we had at the beginning, but I don't think I wrote that number down separately, so I'll just go ahead and say 1/2 and the base and the height. And if you calculate all that, you get 3. Okay, so I just got those points. We will use them later, but that's to show you that if you do a definite integral, it just gets you a number. It gets you the voltage at that point. But the problem doesn't ask for that. It asks us to determine and plot v of t. So that's a function. So we need to come up with a function of t. So first of all, we know that for t less than -4, v is 0. So that's the first part. Our function is going to have 1, 2, 3, 4, 5 different parts to it. So now let's look at the part from -4 to 2. Then that will equal, so now we're going to use the same equation that we did just a minute ago, but now we're going to have our upper limit of integration is going to be t, because we're not going to go all the way to the end of the interval. We want to figure out, well, what is the voltage at any time during this interval, at any time t during that interval. So that will be v of t is going to equal v at -4 plus 1 over c integral -4 to t of I of t dt. Well, now I need to come up with a function for I. So let's take a look at I, and let's get a function for it. Notice it's just a straight line. So to get an equation for a line, you just need 2 points. So I've got these 2 points. I have the point -4, 0, and I have the point -2 and 100 times 10 to the -6. Our slope, it's just a line, so it has our slope. A slope is rise over run. So it goes up by 100 times 10 to the -6 as it goes over by 2. Or our slope is 50 times 10 to the -6. And then if you just go back and remember y minus y1 equals m times x minus x1, and do the same thing here. Our y is I, and our x is t. So it's I minus I1 equals m times t minus t1. So let's just use this point here, right here, which is -4, 0. So I1 is 0, so this gives us I equals 50 times 10 to the -6 t minus t1. Well, t here is -4, minus -4 is +4. So the equation of this line right there, that line, is 50 times 10 to the -6 t plus 4. Okay, so now our voltage equation becomes v of -4 was 0, 1 over c is 5,000, plus the integral from -4 to t of, this is times 50 times 10 to the -6 t plus 4 dt. And if you take the 50 times 10 to the -6 out and multiply it times the 5,000, you get 0.25. And then if you integrate the t plus 4, you get 1/2 t squared plus 4t from -4 to t. And then if you plug in, you get 0.25 times 0.5 t squared plus 4t minus, and then if you plug -4 in, you get -8, so minus -8, or 0.25 times 0.5 t squared plus 4t plus 8 volts. So that is the voltage between time t equals -4, and t equals -2. Okay, so now let's look at the voltage between times -2 and 2. So -2 is less than t is less than 2. So v of t will equal v of -2 plus the integral from -2 to t of I of t dt. All right, well, let's go back and look at our graph. What is our function in here, right there? Well, that's just a straight line. So that's just a straight horizontal line, I equals 100 milliamps. So I of t at that point is just 100 times 10 to the -6. So v of t becomes v of -2, which we calculated up here as 0.5 volts. Now, another thing we could do, rather than have calculated at the beginning, we could have waited till this step and plugged -2 into the equation that we just got. So if we plug -2 into there, we should get 0.5. I'm not going to stop and check that right now. I might have checked it earlier. But the voltage can't change instantaneously in a capacitor, so we should also get 0.5 by plugging it in there. So 0.5 plus the integral from -2 to t of 100 times 10 to the -6 dt. And that becomes, I forgot my 1 over c. I always do that. So that becomes 0.5 plus 5,000. And then you can take that 100 times 10 to the -6 out. So times 100 times 10 to the -6. And we're left with the integral of dt is t from -2 to t. And if you plug that in, let's see, you get 0.5 plus 5,000 times 100 times 10 to the -6 is 0.5. And then this becomes, you plug in t minus, plug in -2 minus -2 plus 2. And so 0.5 plus 0.5 t plus 1 is 1.5 plus 0.5 t volts. So that's the voltage from -2 to 2. So now let's look at the voltage from 2 to 4. So 2 to 4, and we'll have v of t equals v of 2 plus the integral from 2 to t, 1 over c, don't forget the 1 over c, 2 to t of, now we need the equation of this line. Well, it's going to have the same slope as the line over here, just negative. So, and what did we get that slope to be? 50 times 10 to the -6. So this will be minus 50 times 10 to the -6 is going to be our slope. And then t, and you do the calculations exactly the same way. It's just this time we're at a +4 instead of a -4. So this is going to end up being a t plus 4 dt. And then v of 2 we calculated to be 2.5 volts. Plus 1 over c is 5,000. And then you can take out the -50 times 10 to the -6. And then I have the integral from 2 to t of t plus 4 dt. And then that gets me 2.5 minus 0.25 1/2 t squared. I think, let's see, did I make a mistake here? Yeah, this is supposed to be a -4. That's a -4. -4. Minus 4t from 2 to t. Or 2.5 minus 0.25 1/2 t squared minus 4t. And then if you plug in 2, I think you get 6 or -6. So minus negative 6 is plus 6. And I'm just going to leave it like that. You could simplify it, but that's the number of volts. Okay, so, and then also to come up with this V of 2, we had calculated it before, but we could have also have plugged 2 into what we got right here. And sure enough, if you plug 2 into this, 1.5 plus 0.5 times 2 is 1.5 plus 1 is 2.5. You would have gotten exactly the same thing. Okay, so now for t greater than 4, we have v of t equals v of 4 plus 1 over c integral 4 to t of I of t dt. And so v of t equals v of 4, we found out was 3 volts, plus 1 over, not 1 over, it's just 5,000, plus 5,000 times the integral from 4 to t. But when we get out to this region, the current is 0, so then we'll plug in 0 here. So 0 dt, and so that just gets us 3 volts. So this is the voltage for t greater than 4. This was the voltage between 2 and 4, right here. This was the voltage between 2 and negative 2. And this was the voltage between negative 4 and negative 2, and less than negative 4, it was 0.